Okay, in this video we're going to talk about Bayes' theorem. In the last couple of videos I've called it Bayesian techniques. And this section 9 is all about that. We've had a series of 3 videos. This is the third one. And Bayes' theorem uses Bayesian techniques. Okay, so here's the basic setup for Bayes' theorem. We have in the preceding examples and exercises, we're able to start by knowing the probability of A, probability of O, and probability of A given O, and among other things, find the probability of O given A. So the basic idea is comparing 2 trees and allow us to switch the conditional probability around, basically. And this basic concept will lead us to a result known as Bayes' theorem. It's a slightly different collection of known things than the previous stuff, but it's the same basic technique of looking at the 2 trees that makes this work. So the basic setup for Bayes' theorem is that we have a partition of the sample space into n overlapping sets. So forget the red for right now. You have your sample space, which is illustrated by this tan region, and we've broken it up into subsets B1, B2, B3, B4, B5. Now remember, a partition is we've covered everything. Everything in the sample space is in one of those, B1, B2, B3, B4, but exactly one of them. So that none of the B's over B1, B2, whatever, none of them overlap each other. So they're pairwise disjoint, or they're mutually exclusive events, but their union is the whole set. So that's called a partition. And then we have this other set A, this other event that overlaps some or perhaps all of the B's. And it's not necessarily the whole set sample space, but some subset of the sample space. But here it is, and it overlaps some of these things. And we suppose then further that we know each of the probabilities of A given BK. So if we know it's in B1, we know the probability that's also in A. So we know the ratio of basically this piece right here to this B1. And we know the ratio of this piece here to the B2. So we know the probability that it's in A given that it's in B2. And we know the probability that it's in A given B3, and the probability of it's in A given B4, and the probability of A given B5, and so on until we run out of the things in our partition. So suppose we know each one of those, and furthermore, let's suppose we know all the probabilities of the B's. Can we turn around then and find everything else? Can we find, in particular, can we find the probability of A? Can we find the probability, flip them around? Can we find the probability of BK given A? So can we find the probability, if we know it's in A, can we find the probability that's also in B3, for example? And the answer is yes. We can find all the probabilities if we have this set up. And this is how we would do it. So let's do an example that has that kind of situation. Now, basically this is just like what we did in the last couple of videos, in the sense that I'm just going to give you some information. We're going to make 2 trees, two trees. And if we want, we can follow this along with a contingency table at the same time. And we're going to put this into play to figure out our probabilities, at least the ones that we need or want. Okay, so let's say we have a medical example here that we're going to work with, and we're going to have, we know there are 4 types of human blood based on the antigens present. We have O, A, B, and AB. So those are 4 separate types. They're non-overlapping types, and they actually partition the set of blood types. Okay, and for each type, they also can be either positive or negative. Okay, which gives us actually a total of 8 blood types. Now let's suppose we know for a particular population the probability of O is 0.408, probability of A is 0.317, and the proportion of B's in this population is 0.220. We also know these conditional probabilities. The probability that it's positive, if you know it's a type O, is 0.894. The probability that's A, if we know it's positive, is 0.889. The probability of type B, if we know it's positive, is 0.937, and the probability of AB is 0.9 918. And by the way, this data varies a little bit from region to region, but this is some data that I pulled for US data, so it's probably pretty close at least to what's actually happening in the United States. Now suppose we want to flip this around, and what we want to find is, given that we know it's positive, can we flip it around and do this way? Find the probability that it's obla given it's positive, or probability that it's A given positive, or probability B given positive, or probability AB given positive. So let's set up two trees and a contingency table and put in the information we know. So see if you can go ahead and do this on your own now. Press pause. Okay, well, if you look at it, it should look like this. So we've got our blood types here, 0, A, B, and AB, and then we got our two factors here, positive and negative. We know the total's 1. We're given the probability of O, A, and B are these numbers right here. And the conditional probabilities don't show up in the contingency table, but they show up in the tree. Now these three probabilities show up in the tree on the left, where we do O, A, and B and AB first, and then we do positive and negative second. But we also have a tree over here where we do positive and negative first, and then the OA, B, and AB second. So these three probabilities we know, and these three we know. These four we know. Okay, so these four conditional probabilities. So in this type of situation, can we proceed? So yeah, we should be able to fill out a few more things here. In particular, we should be able to fill out this last piece here, which corresponds to filling out this missing AB right here. So go ahead and do that, and then also figure out the probabilities, at least the four that are related to the positive here. Let's go ahead and figure those out at the end of the trees here. So go ahead and figure out those 5 probabilities right now. Well, we know that we could just do one. Well, we could add up the O, A, and B, subtract that from the total 1, or in other words, just do 1 minus 0.408 minus 0.317 minus 0.220, and we get 0.055. So if you add up these 4, you do get 1. That's finding out this last one down here because these 4 have to add up to 1. Now we know that we can multiply the probabilities along the path here to come up with the probability at the end, which is the probability of the intersection. That's the probability that it's both O and positive, which we just call O positive. So then we have probability. Similarly, we can find the probability of A positive, B positive, and AB positive, and those are the 4 things that are right here in the table, these joint probabilities in this particular table. Now, what else do we know? How do these probabilities, do they have anything to do with this second tree? And what about this total right here? Can we do something with that? Well, we know that these same 4 probabilities are the same 4 probabilities that are right here. And notice that the setup of Bayes' theorem is we know all the ones that have a positive on them. So these are the 4 here, which means we know a whole row here. Well, yeah, we can figure out a whole row here. And then we can figure out the total. So adding up this total means adding these up, and that gives us the probability of P here, or probability of P right there. And of course that turns out to be 0.9. Now finally, we're going to figure out these 4 probabilities here. We could go on and completely fill out both trees and the rest of the table if we wanted to. But just doing Bayes' theorem is basically just figuring out these 4 probabilities. So we're going to stop there. Although you could certainly continue on and fill out the entire tree and the entire table. There's enough information to do that. But right now we just need to find these 4. Well, remember, if we put the 0.9 times this probability of O given P, we get this probability of O positive. So we can work backwards by dividing, take the 0.36 divided by 0.9 to get right here. And similarly for the others, and these are the probabilities that we get, 0.4, 0.31, 0.23, and 0.06. These are the probabilities given P of, so this is probability of O given P, probability of A, type A blood given it's positive, probability of type B blood given it's positive, and probability of AB given it's positive are those probabilities right there. And we could fill out the rest of the tree, but those were the 4 things that we were interested in finding, so we're going to stop right there. So you might, just for fun, you might go back and finish up the table and the trees as well. So the way Bayes' theorem works again is this. We have a partition of the sample space into n non-overlapping subsets, B1, B2, up to Bn. We also have a different event A that overlaps some or all the sets in the partition. And we know the probability of A given each of the B's, each of the BKs. And we know the probability of each of the BKs for each K. And using this, we can find each of the probabilities of the BKs given A. And so remember, so this is how it works. The probability of BK given A is the probability of the intersection of BK given in A, BK intersect A, divided by probability of A. Well, we write the probability of A as the probability of B1 intersect A plus probability of B2 intersect A plus probability of B3 intersect A, all the way up to probability of Bn intersect A. And then we rewrite each of these intersection probabilities as the product of a marginal probability, just the probability of a B, and then a conditional probability. So this is probability of B1 times the probability of A given B1 plus the probability of B2 times the probability of A given B2, and so forth. And similarly, we do the intersection probability as the probability of BK given the probability of A given BK. So this guy right here in the numerator is one of these things in the sum at the bottom. It's the one we're interested in. So if we're interested in finding the probability of BK given A, we take that particular one. Like say we're finding B2. We want to find the probability of B2 given A. The numerator then is probability of B2 times the probability of A given B2. And the denominator has all of these added up, the probability of B1 times the probability of A given B1 plus the probability of B2 times the probability of A given B2, and so forth. Now, this is Bayes' theorem, this in red. Okay. Now, personally, you can memorize it if you want. You can try to apply it. But at least for the purposes of my class, I don't expect you to do that. I don't even expect you to write it down and use it. What I would like you to be able to do is make sure that you understand how probability trees work well enough to basically take the given information, put it in this tree, and figure out what you need from this other tree here by doing the interplay of the two trees. That's rather than just memorizing some formula and plugging it in. This shows that you understand what's going on with probability, and that's the main thing that we're going to do there. So that's in a way, that's one of the more complicated things that we're going to do this semester, is work with these two trees back and forth. But if you really understand how trees work, it's really not too hard. It takes a few minutes to do for sure, so it's not a real quick problem, but I think it is one that you guys can do with a little practice and with no problems.